So we're going to start with example 2 now, writing the terms of a sequence. I want you to write the first 5 terms of the sequence given by a sub n equals negative 1 to the nth power over 2n minus 1. First 5 terms, we start with 1. So a sub 1 equals negative 1 to the first over 2 times 1 minus 1. Well, negative 1 to the first is negative 1 over 2 times 1 is 2 minus 1 is 1, we get negative 1. A sub 2 is negative 1 squared over 2 times 2 minus 1, we get 1 over 3, 1/3. A sub 3, again, same thing. Okay, sorry about that. Okay, so a sub 3, we've got negative 1 cubed over 2 times 3 minus 1, negative 1 over 6 minus 1 is 5. A sub 4, negative 1 to the 4th over 2 times 4 minus 1, negative 1 over, positive 1 over 7. And a sub 5, we have negative 1 to the 5th over 2 times 5 minus 1. And you're going to get negative 1 over 9. So the way to write all this, so that it's easy to see, clear, legible, negative 1, comma, 1/3, negative 1/5, 1/7, negative 1/9, dot, 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 end of the parentheses, okay? Let's look at how to graph these on your calculator. To graph a sequence on your calculator, you're going to hit mode, sequence, and DOT. So dot stands for dot. So sequence, dot, and then you can graph those using your y equals. Okay. Slide 7, example number 3, finding the nth term of a sequence. Write an expression for the apparent nth term, a sub n, of each sequence. Well, how do we do this? Let's look here. 1 to 3. What are we doing between 1 and 3? I think we're adding 2. Again, adding 2, adding 2. So it looks like every time we're adding 2. So if we start with, this is our rule. Rule is that we add 2. So 2 times our nth power. And we start with 1. 2 times 2, right? That's our rule. Or 2 times 1 is 2. And then we're subtracting 1 to get that 1 there. So our rule, our expression would be 2n minus 1. So if you plug in your a sub 1, you get 2 times n, which is 1, minus 1 equals 1. Okay, again, do that little check at the end. So you have 2n minus 1 here. And let's look over here. 2, 5, 10, 17. Well, now it looks like we're jumping a little bit. So we go plus 3, plus 5, plus 7. Okay, it's going up kind of quickly. And it looks like we're adding odd numbers. Add odd numbers. Well, let's write out our n's. We've got 1, a sub n, 1, 2, 3, 4. We've got 4 terms here, so we'll write 4 of them here. And then we're going to write our a sub n's. What's our answer? We've got 2, 5, 10, 17. And what changes between 4 and 17? What's the number there? What can we kind of tell looking at all of this information? Well, I notice that if I had 1 plus 3, well, that's 4. That's not what I want. I really have a 2 here. What about if I did 1 squared? Let's throw everything off for a loop here. 1 squared. Well, 1 squared plus 1 is 2. Okay, what about 2 squared? Well, 2 squared is 4, plus 1 is 5. 3 squared is 9, plus 1 is 10. And 4 squared, that's 16, plus 1 is 17. So, if you notice, we've got n squared plus 1. Okay, and it takes a little bit of time to kind of notice the patterns, and again, really important that you can recognize what you're doing with your numbers. Okay, we also have something called a recursive sequence. We're almost done for today. They can be defined recursively. This means that each term is defined using the previous term. So if a sub 1 is 1, a sub k is equal to a sub k minus 1 plus 5, which means that if I had, let's say, 2, I wanted to find out what the second term was, but I only knew what the first term was, I can plug the 2 in here, and I would have a sub 2 minus 1. Well, that gives me a sub 1, hence why I'm able to do this. So in this sequence, a sub 1 is 1, plus 5 is what? 6. Okay. Now what if I plugged in a sub 3? Well, a sub 3 minus 1 is a sub 2, which we already know is 6 plus 5 is 11, so on and so forth. Okay. Again, make sure you designate what yours looks like in a nice, pretty little parenthesis set. Okay. All right. Number 9, slide 9. Okay. Example 4 of the Fibonacci sequence, a recursive sequence. This is recursive. The Fibonacci sequence is defined recursively as follows. A sub 0 is 1, a sub 1 is 1, a sub k is a k minus 2 plus a k minus 2, the sum of the previous two terms. Now this is a pretty famous one. I'm sure most of you have heard of it. Let's write out the first 2 terms, or first 6 terms, excuse me. They've already given us a sub 0 and a sub 1. A sub 0, we've got a to the k minus 2, oh, sorry, it's right there. A sub 1 is 1, a sub 2. Okay, well, 2 minus 2 is 0, right? A sub 0 we already know is 1, and k minus 1, 2 minus 1 is 1, a sub 1 is 1, so 1 plus 1 is 2. A sub 3, we have 3 minus 2 is a sub 2, which is 2, plus 1, we get 3. A sub 4, okay, we plug in, we get 3, plus 2 is 5. Alright, and then we have a sub 5, so we're going to have the 5 plus 3 is 8, and last term of our sequence, a sub 6, we've got 8 plus 5 is 13, and just to be fun, a sub 7, we've got the 13 plus 8, which is 21. Okay, and that's it for the Fibonacci sequence. We're going to be moving on to factorial notation. We've got 3 more slides to go, you guys. Hold on tight. Okay, so next page of notes, we've got factorial notation. Definition of factorial. If n is a positive integer, n factorial is defined as n with the little exclamation mark, 1 times 2 times 3 times 4, da 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 da. And the way you would write this sequence is n minus 1 times n. Note, 0 factorial is equal to 1. Okay, I'm sure you all have seen this before, heard it before. It's kind of fun because they can expand really well, and they're really fun when you get to start simplifying them. Okay, so writing the terms of a sequence involving factorials. I want you to write the first 5 terms of the sequence given by a sub n equals 2 to the nth power over n factorial. Okay, so let's start at a sub 1. Oops. Hello. Okay, a sub 1, I've got 2 to the first over 2 factorial. Okay, well 2 to the first power is just 2 over 2 factorial, which is 2 times 1. So I get 2 over 2 is 1. Then I have, okay, so now we have a sub 2. We have 2 to the second power over 2 factorial. So I've got 2 squared, which is 4, over 2 times 2. Oh, hold on. What did I do wrong? Where did I get this 2 from, ladies and gentlemen? Am I just making numbers up right now? Okay. So, this should actually be 1 factorial, which is just 1. So I have 2 over 1, so it's 2. There we go. And 2 factorial, that makes more sense. So this should be 4 over 2 times 1, which is 4 divided by 2, which is 2. Okay, a sub 3, I have 2 to the third power over 3 factorial. Well, that's 8 over 3 times 2 times 1. So 8 6, simplified to 4 thirds. We have a sub 4 equals 2 to the fourth power over 4 factorial. 2 to the fourth is 16. 4 factorial is 4 times 3 times 2 times 1, which is 24. So 16 over 24. You can divide both by 8, and you get 2 over 3. Then we have a sub 5. We have 2 to the fifth power over 5 factorial. I get 32 over 120. 5 times 4 times 3 times 2 times 1. And divide top and bottom by 2. You get 16 over 60. Divide again by 2. You get 8 over 30. Divide by 2 again. You get 4 over 15. So the terms of this sequence, if we were to write them out, is 2, 2, 4 thirds, 2 thirds, 4 15ths, dot, 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 dot. Okay? And that's the first 5 terms of the sequence. Okay? Let's look at, next slide, evaluating factorials. Okay? Evaluate each factorial expression. So let's work these out. If I were to write this out, it would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. If I were to write the bottom ones out, I have 2 times 1 times 6 times 5 times 4 times 3 times 2 times 1. What do you notice is the same on top and bottom? Well, I notice that I have my 6 times 5 times 4 times 3 times 2 times 1 over my 6 times 5, blah, 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 blah. They all cancel. And then I notice I have an 8 and a 2. Well, I can divide 8 by 2, and that's 4. So I'm left with 4 times 7, or 28. Okay. Over here, I have 2 factorial times 6 factorial over 3 factorial times 5 factorial. So 2 times 1 times 6 times 5.